Welcome dynamics students. This mini lecture will involve the groundwork for what's known as particle impact. So this is a subset of particle impulse and momentum, and it's reserved for very high rate collisions where we definitely have a certain amount of deformation, both in one direction as particles approach one another, and then again as they spring apart. So we're going to indirectly, without really getting into the nitty-gritty of mechanics of materials and material deformation, we're going to use an empirical measure of the nature of that deformation and in fact how elastic it is, to what extent the energy of deformation is fully recovered or not, to give us additional information to solve a conservation momentum question where we maybe don't have all the information. So let's start out. The term impact refers to collisions that are very, very high rate and have enough force involved in the impulse associated with the collision to actually deform the materials that are involved. Again, we can have plastic deformation, which is permanent, or we can have elastic deformation, which is 100% recoverable. It's reversible. So those are the key essentials of what makes a collision an impact or not. Obviously, there's some gradation there. What would be considered an impact for one material might not for another. Okay, during an impact, conservation of linear momentum applies. So ultimately, the particles going in, you can sum their linear momentums. You can look at the particles exiting the impact collision, sum their linear momentums. Nothing will have changed, basically. So we can still write that as conservation of momentum for the whole system. But quite often we'll know both masses. So we'll have mass 1, mass 2. We'll have the velocities of the particles coming into the collision, and we're going to need to solve for the velocities of the particles coming out. Conservation of momentum gives us one equation. M1v1 plus M2v2 equals M1v2 or M1v1 after plus M2v2 after. So we'll have two velocities post-collision that we can't solve for in only one equation. So we're going to use something about the nature of that material deformation during the impact and some nice impulse momentum considerations throughout the steps of the impact to create some expressions that will give us another equation that we can use to solve, that we will use in tandem with our full conservation of momentum pre-post. Okay, and to do that we're going to use a little schematic, which I will blow up. Okay, so we're looking at the steps of the collision. So initially we've got two particles, and particle A is going to overtake particle B. So obviously, for there to be a collision at all, VA1 has to be bigger than VA2. So they're both moving in, we'll call this the positive I hat direction. And so their velocities are both in the positive I hat direction, and VA1 is bigger, so they're going to collide at some point. When they do, as the collision starts, the particles are going to touch and they're going to smoosh into one another. And as they do, Newton's third law says they're going to exert forces on each other, collinear, equal, and opposite. Well, that means the time integral of those forces is also going to end up being equal and opposite. So the impulse of A on B is equal to the impulse of B on A, but going the other way. So if we've defined to the right on this page as the positive direction, positive x direction, and the positive direction for our velocity, we could say that the impulse exerted by particle A on particle B is in the positive direction, and it's some pressure force. We'll call it P because we can think of the particles having pressure they're exerting on each other, integrated over some time, is the same, equal and opposite, to the same force integrated over the same time but pointing in the other way if we're looking at the impulse exerted by B on A. So equal and opposite. At some point they've deformed as much as they're going to. Their centers of mass are as close as they're going to get. This is the point of max deformation, and at that instant they have the same velocity. They've now come into coincidence velocity wise. Nothing is moving relative to anything else, no relative velocity. So we have 1v. So that's going to be a point we use to make our mathematics more solvable. There's that single variable that they both share. Then the opposite is going to happen. They're going to rebound somewhat. So the extent to which they will do so is dependent on how elastic the collision is. So if the materials are fully elastic, they follow Hooke's law, this recovery will be almost the same as the initial deformation. And we'll get into a nice empirical measure of how true that is. But this is called the recovery phase. So again, now the particles are still pushing on each other over some period of time. And again, even though they're pushing back, they're still pushing on each other. So the impulse during recovery of A on B is still pushing in the positive I hat direction. And the impulse of B on A, even though it's recovery, and then the particles are moving in a different direction relative to one another, is going to be still going in the opposite direction, although it'll be lessening with time probably. Kind of like a spring that's returning. It's still pushing back, but it's getting less with time. And then at some time at the end of this impulse, integrating from T1 to T2, after T2, they're going to be going off with their post-collision velocities, so VA2 and VB2. In most problems, we'll know the incoming material, the incoming velocities and masses, so the incoming momentums. We won't know the exiting velocities. But if we know something about the nature of the materials, we'll know something about the ratio of this to this. So this is where we'll invoke some kind of material property. And that material property is called the coefficient of restitution, otherwise known as little e. So it's the ratio of the restitution recovery impulse to the deformation impulse. So the more elastic this is, the closer it is to 1. The more plastic it is, the closer it is to 0. So we can use E along with this single velocity V at max deformation and write momentum impulse expressions for each particle, and then use some knowledge we're given about the coefficient of restitution to give us enough equations and unknowns to solve the problem. So we can start with particle A, and we're just going to we're going to walk through the impact from the point of view of particle A. So it's starting out with its linear momentum initial, MA VA1 going in the positive I hat direction, and then it's going to start into the collision, and it's going to be acted on with a force impulse from particle B, and it's going to get to the midpoint of the collision with its mass going at this common velocity at a point of max deformation. So initial linear momentum at this midpoint, difference being whatever the impulse was coming from particle B. Now we're going to start in the middle and go to the end. So we're going to say, all right, we're starting in the midpoint of this impact. So we got our mass A, our particle A is moving at this common max deformation velocity V, not B. Okay, it's going to continue to get acted on by an impulse force going in the negative I hat direction during the recovery phase. Particle B is still pushing on it, and so it's going to exit the collision with VA2. So we've got, if we assume we know the mass, We've got three things we may or may not know in terms of velocity. We've got an initial, we've got that midpoint velocity at max deformation, and we have our exiting. We're assuming we know V1. That's pretty common. We have no way of making an expression for this impulse and this impulse, but we might know the ratio. We'll assume we know the ratio in this coefficient of restitution. And we have this max deformation velocity we don't know. We can rearrange this whole expression and this whole expression to allow us to use this ratio. There's something that we should be able to look up in a table for a given type of impact and materials considered, and then use it such that we only have V at max deformation and VA2. It's still not enough to solve for everything we know, but we can do the same thing for particle B. We can walk particle B through the collision the same way, except in all cases, rather than being pushed back on, it's being pushed along by particle A. So the signs have changed from the viewpoint of particle B. It enters with VB1. As it gets subject to the deformation phase of the impact, it's being pushed forward by particle A, and so it will speed up. We would expect this V at max deformation to be more than this V to be more than VB1. And that will continue through the recovery phase all the way out to VB2. So we would assume that our VB2 is going to be greater than VB1. And we can apply the same coefficient of restitution because, again, our impulses are the same. They're just going in the opposite direction. Newton's third law is applying here. And what we end up with is enough equations by using our known value of E for the coefficient of restitution, the knowledge that this V at max deformation is the same for A and B, and what effectively becomes expressions for conservation of linear momentum. And we now, if we know all of those things and we're willing to rearrange the math, if we know VA1 and VB1, and we know E, got a lot of red showing up here, we can use all of these expressions to get VA2 and VB2. We effectively, by invoking the properties of the steps of the collisions, we add a variable in the form of this velocity at max deformation, but we give ourselves two additional equations. So we end up with, instead of one equation with two unknowns, we end up with three unknowns and three equations by invoking the properties of the impact collision in all of its steps and a knowledge of that coefficient of restitution. So just like in statics, where we had to use the definition of friction to give us an additional piece of information, sometimes to solve for all the unknowns that we had, we're using additional information about the nature of the impact in terms of the nature of the deformation and recovery. Is it elastic? Is it inelastic? To solve for all of our momentum expressions, namely our velocity expressions. This presumes we're not losing any mass. That is kind of an unwritten rule that MA going into the impact is equal to MA coming out of it, and likewise for B. So far we haven't considered any mass loss as a result of interparticle interaction or force impulse. So I do not have an example for that. I've just laid out the general properties. There will be in other parts of this course some examples either are written or done in one of your live synchronous classes, likely, where this concept will be tried. In most cases you will be given incoming velocities, need to solve for exiting, or you'll be given and you'll have a coefficient of restitution, or maybe you'll have entering and exiting and need to solve for a coefficient of restitution. Irrespective, remember, conservation of momentum prior to and following the impact still works, and that we are simply getting more information about what's going on during the collision in order to give us more equations to solve for the unknowns in addition to our conservation of momentum. So that is impact in a nutshell.